Welcome back. Today we talk about complex numbers and polar coordinates. We just had our 8th quiz, and you should hopefully be working on Project 8, which will be due in just a couple of classes. Okay, also want to point out at this stage that the required form number 3 is coming up, so you might think about doing that early if you have time to do so. Complex numbers have the form z equals a plus bi, where I squared is -1. A is called the real part, and b is called the imaginary part. So if you've, so hopefully you've seen some complex numbers before. It's just a larger number set that contains all the real numbers plus many non-real numbers. Number 2, adding and subtracting complex numbers is straightforward. We'll do one division, which will include a multiplication. Let's find and simplify 1 plus 2i over 2 plus 3i. So the question is, what is there to do? I mean, there's a perfectly good number where there's some complex number on top and another complex number on the bottom. So mathematicians just have a policy that they don't like having i's in the denominators of fractions. So we're going to do something quite funny in order to make it so that we don't have i's in the bottom. I'm going to multiply the bottom of this fraction by 2 minus 3i. And we'll see why that's the right thing to do, but I'll just say it's the same as the bottom, but changing the number that's in front of, changing the sign of the number in front of the I. It used to be 2 plus 3i, now it's 2 minus 3i. But if I do that to the bottom, I better do exactly the same thing to the top. So make sure you don't put on top 1 minus 2i, that's not the idea. You got to do the same thing top and bottom. And we always choose to do this based on the bottom. The top is kind of irrelevant. Okay, so what we're going to do, I'll put parentheses here just so we really see that we're foiling. So we're going to FOIL upstairs and downstairs. 1 times 2 is 2, outers minus 3i, inners plus 4i, lasts minus 6i squared, divided by outers, firsts, 4, outers is a minus 6i, inners is a plus 6i, lasts is minus 9i squared. Okay, now we're going to start combining some stuff. So 2, combining the like terms that we have here, minus 3i plus 4i is a plus 1i. And then the next thing is this minus 6i squared. Well, I squared, according to what we had up above, is -1. That's right there. It's basically the definition of I. So that I squared is really -1. So -6 times -1 is really a plus 6. So this becomes a plus 6. Divide by. Okay, that was so much fun. Let's do the same thing for this guy. Again, I squared is -1. So subtract 9 turns into a plus 9 there at the end. The inner and outer terms, minus 6i plus 6i, cancel. And the whole thing just becomes a 4 plus the 9 on the bottom. Equals, let's combine terms upstairs, 8 plus I divided by 13. So that answer is fine. Oftentimes we want our complex numbers to look like a plus bi, so a number plus another number times I. And if that's the case, then we need to split this up into 2 fractions. And if we really wanted to peel the I off so that it's next to a number, then we have to rewrite this, as 8/13 plus 1/13 times I. Okay, so that one right there is simplified. I mentioned that we would do multiplication. We did. You just do multiplication of complex numbers by foiling or distributing. And then we made use of our important identity here. I squared is -1. And then eventually wrote it as a plus bi. That's our standard form for complex numbers. And I just want to show you that we accomplished our goal. We didn't like having the I in the denominator of our fraction. This thing right here is just a real number with no i's in it. So why did multiplying by 2 minus 3i work? Well, because that's the only thing that's going to give you this cancellation here in the middle, right? 2 plus 3i, 2 minus 3i gave you exactly the same 6i in the middle, 1 negative, 1 positive. So that's why that's the right thing to do. I also want to show you that your calculator can do all of this. So if we type in this thing right here, so parentheses 1 plus 2i, so the I is right above the decimal point here, so second decimal point, divided by parentheses 2 plus 3i. And then we'll hit equals. Now we're going to get some crazy looking decimals here in a second. So there they are. So we got this 0.6 and change plus a 0.07. Now there's a ... there. I claim that this answer is equivalent to the one we have. So that 0.6 and change, is, okay, that's reasonable. 8/13 could be around 0.6. 1/13 could be around 0.07, but what's missing here is this I. But the dot, 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 maybe you haven't seen it on this screen before. You can hit the right arrow, and it will scroll you through lots of decimals, and then eventually the I that we wanted right there. And so if you wanted to double check that, that this was right, you could type 8/13 right here and confirm that it agrees with all the decimal stuff that we got there, and then type 1/13 and you'll get this. Or you could just hit math, and the very first one says convert the previous answer to a fraction, and it will give you 8/13 plus 1/13 I. Even though it looks like the I is on the bottom, we know order of operations says it's really next to the fraction, which essentially makes it upstairs. 3, the complex conjugate, this is a definition, of a plus bi is a minus bi. And it's given a special name because it's important when you want to get rid of the imaginary parts. So 2 plus 3i had a conjugate of 2 minus 3i. And it's denoted a plus bi with a bar over it. I don't think we're going to use that notation, but just in case you see it somewhere else. So for example, you could say that 2 plus 3i, the conjugate of that is 2 minus 3i. 4, we can plot complex numbers as points in the complex plane, which looks an awful lot like the xy plane. So the xy plane has the x-axis and the y-axis. Well, we don't have that anymore. Now it's the real axis and the imaginary axis. And if you have a point over here and it's sitting above some number a and to the right of some number b, what we're saying is that this is how you plot the point a plus bi. So the a is just the real part of the number, and so you go to the a on the real axis down here, and the b is the imaginary part, so you go to the b on the imaginary axis. The I doesn't show up any place other than the fact that we're saying this vertical axis is the one that is associated with the I. And so when we plot it as a point, it's just the point a comma b, right? A comma b. And you just plot it normally, the I is just kind of absorbed in our name of that axis. It's not the y-axis anymore, it's the imaginary axis. 5, let's plot 3 plus 2i. So 3 plus 2i is really the point 3 comma 2. The I doesn't play into it, so we just go to the point 3 comma 2 and we say, look, we have been really fancy and plotted the point 3 plus 2i. Next one is negative 5 minus 3i, minus 5 minus 3. Negative 5, negative 3 is down here, and that's the point negative 5 minus 3i. And then finally just I. Okay, so in order to plot just plain I, we need to write it as a plus bi. So this is really 0 plus 1i. And so then if we're plotting that as a point, it's 0 comma 1. So that right there is the point 0 plus 1i, or simply I. 6, we can also convert the coordinates of a point to polar coordinates by using the formulas from the last section. Pause the video here, see if you can remember these formulas, and then come back when you're ready. Okay, hopefully we remembered them. R equals square root of x squared plus y squared. Theta was the inverse tangent of y over x. We're not going to use those ones too much today. We're going to use these ones. X is r cosine of theta, and y is r sine of theta. So let's use those formulas on the next page. Let's convert negative 5 minus 3i into polar coordinates. So again, we're thinking of the x as being the first number and the y as being the second number, not including the I. And so then we're going to go into polar coordinates. And I guess this means I lied. I said we weren't really going to use these formulas, but here we are using them. So we've got this one and we've got this one. So the first one says take the square root of negative 5 squared plus negative 3 squared, 25 plus 9, 34. And then inverse tan of, what do we do here? Negative 3 over negative 5. So let's type that on the calculator to get a decimal. Okay, whether you're in degrees or radians is not specified in this problem. I'm going to bail on radians just for the time being because we're a little more comfortable in degrees. But let's type this thing into the calculator. Inverse tan. So you don't need to type the negatives because, of course, they cancel, but I'll just type it. So we get about 31 degrees. So that's about 31 degrees. And then let's get a decimal here, something like 5.7. Let's see, square root of 34. 5.8. Okay, so what does that mean? Well, let's go back. So 5.8 and 31 degrees. So let's go back to this picture right here and take a look at the point -5, -3i. So then what we said is that -5 minus 3i is really supposed to be, I don't know how to write it. Okay, we don't have a way to write it just yet, but -5, -3 in xy land is apparently about 5.8, 31 degrees in r theta land. Okay, let's see if we believe that. So we would go to 31 degrees. So 31 degrees ballpark is like there, 31 degrees. And then 5.8 away, let's see. So if we go out to here, that's a little bit more than 5. So maybe here-ish, something like that. And is that right? Well, -5, -3, it's not anywhere in the first quadrant. We plotted it already. It's down here. Oh, we made a mistake. This 31 degrees doesn't make sense given that we need to get down here. And it's because inverse tan is defined the way it is. It will never give you an angle in the third quadrant. It'll only give you one in quadrants 1 or 4. So what we need to do is change that 31 degrees because it doesn't make sense in the scope of the problem. So we got to say, okay, it wasn't 31 degrees. It was really 31 plus 180. So what is that? 211? Okay, let's go back and graph that one. So 211 degrees is just the opposite angle from the green line that I drew. Okay, my angle wasn't quite perfect. I guess really it should have been more like this kind of thing. And is it reasonable to say that the length of that blue line segment is about 5.8? Sure, why not? So we're finding the same, we're plotting the same point. See, I don't want to lose that. Plotting the same point as we did before, but just putting it in the newly familiar polar land, polar way of looking at things. And there's going to be a real good reason for us to prefer polar to the XY coordinates today. Okay, so we've done that. And then we come down here, 8. We observe that x plus iy is equal to r cosine theta plus I times r sine theta. Let's pause there and make sure we believe it. Well, let's see. We did see the equation just a moment ago that x is equal to r cosine of theta. And we also saw that the y was equal to, out there, the y is equal to r sine of theta. And I don't quite have room to do any more highlighting, so I'll just circle the I is copied over here. Okay, so we should believe that first equation. And then in the next step, we can factor the r out because there's an r in both terms. And then we just get cosine theta plus I sine of theta. Okay, fair enough, which we may abbreviate r cis of theta, one of the stranger acronyms you will ever see. So r cis theta, r cis theta, stands for r, there it is, times cosine, there it is, plus I, there, times sine, there, both of these guys of theta. So this little guy right here stands for r cosine theta plus I sine of theta. So maybe we'll highlight in green. This little thing represents this whole big thing. Okay, so let's use this formula to find another way to write -5 minus 3i. Okay, so -5 minus 3i is equal to, so it's an r in the front. Now the r we just found up above was 5.8, roughly. 5.8 times cosine of the theta, that was about 211, plus I sine of theta, 211. So all we did was use our nifty little formula here that says x plus iy is really r times cosine theta plus I sine of theta, provided you get the right r and the right theta. So is there any reason you should believe that? Well, sure. Let's take a look and see if the calculator can confirm. For example, if I distribute this 5.8 into the cosine, so we go 5.8 times cosine of 211 degrees, I claim that we're going to get something darn close to this -5. And that's darn close. How come it's not perfect? Well, it wasn't really 5.8, it was this. And it wasn't really 211, it was really 210.9637. And if I do the same thing, but instead I think about distributing the 5.8 over here to the I sine of 211, and I hit enter on this one, and I get -2.98, which is darn close to -3. So that guy times this guy will have an I in it, which is there, and something very close to -3. So yeah, actually this looks like it's true, just rounding errors. And then we'll use our nifty green highlighted thing to abbreviate the right-hand side to, let's see, R cis theta, 5.8, funny acronym, 211 degrees. So when I say that -5 minus 3i is equal to 5.8 cis 211, I really mean they're equal, because if you distribute it here, this guy and this guy, then you get exactly what you think. And all we're doing is abbreviating the stuff in the parentheses. Number 9, why is this useful? Because of a result called Eulers Formula. I know the word looks like Euler, but it's actually pronounced Euler. He was a Swiss mathematician. I think he lived for most of the 18th century, something like 1707 to 1790-ish. He lived to be pretty old. So here's his formula. E to the I theta equals cosine theta plus I sine of theta. And then the left-hand side should look crazy. I don't know what's going on there. But the right-hand side, cosine theta plus I sine theta, that's cis of theta. That's just like with a 1 in the front, right? So that's okay. According to this formula, what is the value of e to the I pi? Well, let's try. E to the I pi equals, okay, let's see. So here's the formula. E to the I theta is really cosine theta, so cosine of pi plus I sine of pi. Okay, cosine of pi, that's -1, plus, and then sine of pi is 0. So I times 0, or just -1. So that means that e to the I times pi is -1. Now, what does it mean to take e, so that's like our 2.7 number, and raise it to an imaginary number? It's not clear, and in fact, we're not going to really give meaning to it. But somehow these three magical constants, e and I and pi, which are arguably amongst the three most important mathematical constants, they work together in some strange way and give you some really nice number, -1. So honestly, this equation right here is my absolute favorite equation in all of math, and I'm sure you have yours, and we can debate about the merits of yours and mine. Some people prefer to add 1 to both sides, and so that allows them to get the additive identity, right? 0 is a special number with a property that says if you add it to anything, then anything doesn't change. And the multiplicative identity, because multiplying something by 1 doesn't change the something. And so now they argue that we've got these three famous constants, and then this famous constant, and then this famous constant, and maybe the 5 most famous constants all in one equation. I say hogwash. It's artificial to move the 1 over to the other side. So I'm content to just have my 3 nice constants, e, I, and pi in one equation. I'm not going to get greedy. 10. We will not discuss the proof of this formula, which requires calculus, or examine what it means to raise a number to an imaginary power. What is important to us is that we can manipulate complex exponentials, such as e to the I theta, using the usual laws of exponents. We can use Euler's formula to rewrite any complex number as a power of e. X plus iy equals r cis theta, we saw that. But now, apparently, according to Euler, cis of theta is really the same as e to the I theta. So cis theta just becomes e to the I theta in this formula. Maybe we'll highlight those two things, cis theta and e to the I theta. Okay, so you should be honestly pretty confused at this point because there's so much new notation and then this crazy idea of taking e and raising it to an imaginary number. But the techniques that I want you to be able to do are actually not that hard with a little practice. So let's try our first one here in 11. Let's use this formula to rewrite -5 minus 3i. Okay, so Negative 5 minus 3I equals. All right, so the first thing we wanted to do, let's take it and write it in r cis theta form. Well, we actually did that up above. It's there on the far right-hand side, 5.8 cis to 11. So there was work involved there. We had to use the r equals square root of x squared plus y squared equation and then the inverse tangent business to find theta. But now we get into Euler's new business, which says that if you have r cis theta, you can just write that as re to the I theta. So this is really equal to 5.8, that's the r, e to the I times theta, 211 degrees. So we now have a new way of writing things. Negative 5 minus 3I is apparently equal to 5.8 e to the I times 211 degrees. Now, how is that useful to us? Well, let's answer number 12. Let's find negative 5 minus 3I to the sixth. Okay, so first, the old way, the only way you have if you don't use the techniques from today, is if you're going to take negative 5 and subtract 3I and raise it to the sixth, that really means negative 5 minus 3I times negative 5 minus 3I, and we need to write 6 of these, right? Negative 5 minus 3I. Okay, so I'm already tired of doing this, and I haven't even done any of the work yet. The work is like this massive distributive property, right? So first you can FOIL these two guys together. So this times this, and this times this, and that times that, and that times that. So then you get a bigger thing in here. It would be a trinomial. And then for every term in your trinomial, you then have to multiply by this, and this, and this, and this, and then the last term times this, and this. And that gives you a term with, an expression with 4 terms in it. And then you got to keep distributing, or maybe you distribute over here separately. It's just a huge distributive problem. And I certainly don't want to get involved in that. So let's do the new way, the improved way. Okay, so instead of doing negative 5 minus 3I and raising it to the sixth in the old way, we're going to rewrite the negative 5 minus 3I. Apparently, negative 5 minus 3I is equal to 5.8 e to the I times 211 degrees. So that's what we saw right up here, right? 5.8 e to the I times 211 is the same as that, which is the same as that, which is now in here. Aha, but we have a property that says, for example, if you want to take like a times b and raise it to some power, you can take that power and in a sense distribute. I don't like using that word, but the power comes in and hits both of the, or all of the factors inside the parentheses. So let's try that here. So this is equal to, so the sixth power comes in and hits the 5.8, and it also comes in and hits the e to the I times 211. Okay, moving on, let's see, 5.8 to the sixth, I'll just copy that. But then we've got this other property of exponents that says if you have a to the, let's see, how do we write this? A to the x, the whole thing raised to the y. And what do we do with those exponents? Well, you know that we multiply them. So that's what we've got going on here, because we're going to take the sixth that's out there, that's like the y, and we're going to multiply it by this stuff, which is like the x. So this becomes e to the, okay, so 6 times 211, what is that, 1276? I. That is not right. 1266. How's that? 6 times 2 is 12. 6 times 11 is 66. Okay, so we've got e to the 1266i. Super. 5.8 to the sixth, we can type that on the calculator. Okay, but here I really do want to go back, instead of rounding to 5.8, I want to go back up to that number. So let's do our second square root of 34. And then we're going to take this number and raise it to the sixth power. No, it turns out to be an integer. It's kind of surprising, but maybe not if you think about where that 5.8 came from. So this is really equal to 39,304. Okay, and then we've got this e to the 1266i. Well, it would be strange to write the final answer in this e to the I theta form, given that the original problem was just an x plus iy. So how about we go back? So I'm just going to copy this guy for right now, 1266i. But how about we go back and again use Euler's formula, but now the other direction. If we see a, where is it? Just off the screen here. If we see e to the I theta, we could think of it as coming from a cis theta. So how about we do that? So this is really 39,304 times cis of 1266. So e to the I theta becomes cis theta. So that was this piece turning into this piece. Okay, but then what does cis really mean? Well, let's go back to that definition. Ultimately, I'm just trying to get to x plus iy. So this equals 39,304 times, okay, cis. C was the cosine, I was I, S was the sine, and then 1266 is the theta, so that goes into both. And there was a plus sign built into the cis formula, what cis means. Okay, and here we are. I can type in cosine of 1266 and get a decimal. Same thing for sine of 1266. So let's do that now. But again, instead of using 1266, I'd really like to use the non-rounded version of things. So let's give this a shot over here. So where did the 1266 come from? Well, it came from the 211. So where did the 211 come from? Well, that one came from the inverse tan. So let's go back and do this inverse tan business. Inverse tan, I think we were at -3 divided by -5. So we should get about 31 degrees. Okay, so that was that. But then we added 180 to that because the calculator misled us and gave us something in the first quadrant when it should have been in the third. So there's our 211. I multiplied that by 6 because we multiply when they look like that. And we got something around 1266. So I want to use this number a couple of times. So I'm just going to store this as x. I'm going to store this as a. And let's go ahead and find the cosine and sine of that number. So we want cosine of a, which is that, and then we're going to multiply that by the 39,304 because this 39,304 will distribute. In fact, I'm gonna write this out. So let's, what do I want here? Cosine of a and sine of a. Okay, so this equals 39,304 times, what did we get first? -0.9949 plus I times -0.10075. Let's see, so put that in parentheses. Okay, and then we're going to distribute the 39,304 into both terms. And so let's do that here. So I'm going to multiply that guy by 39,304. And then we get that nice number, which is kind of surprising because it was quite not nice in the beginning. And then we'll go ahead and do the 39,304 times the cosine of a. I don't want to retype. I want as accurate as possible. So I get that. Okay, so this is equal to, what do we start with? -39,104 plus, there's an I there, I, times -3960. So I'm going to put the 3960 and then I'll erase this guy here and make it a minus 3960i. Okay, and so this is now our final answer in the form a plus bi. Whew. Okay, so what did we accomplish? Well, we took -5 minus 3i and we raised it to the 6th power. And we did that without having to actually do the massive distributive law. Like it might have felt like this was a lot of work. I guess it was. But compared to the distributive stuff you have to do here, this was a walk in the park, let me tell you. So did it actually work? I mean, if we had done the whole distributing thing, would we have gotten this -39,104 minus 3960i? Well, I don't know. Let's see. Let's see what the calculator has to say about that one. So let's go back up to the original problem. -5 minus 3i to the 6th. -5 minus 3i, whole thing raised to the 6th power. Now, I don't want us to be disheartened by what's about to happen, but in a very short amount of time, we're going to get the answer to our problem. Now, the calculator is, I think, doing some kind of massive distributing thing. Now, let's see what it says here. Negative 39,104 minus 3960i. Okay, so on the one hand, that's comforting because it means we did it right. On the other hand, goodness, that was a lot faster than what we did, but that's okay. When you're on your deserted island, you won't have your TI product, and so you'll need to be able to do this stuff in the sand by hand. Next page. 13, let's find the eighth root of negative 5 minus 3i, as well as a few other eighth roots of negative 5 minus 3i. Okay, so we're going to do this in two ways. So we're going to do the easy way first. Okay, so the easy way first. So we got the eighth root of negative 5 minus 3i. What does that even mean? I have no idea. So how about we rewrite this negative 5 minus 3i in one of the alternate forms? We've written that number in many, in three different ways today. So one of the forms that we had was this 5.8 cis 211. But having that thing under a square root would still leave me baffled. But what if we come down, or I should have said eighth root, but what if we come down to the e version of this number? So negative 5 minus 3i is really this guy, and so maybe having this under a radical, I don't know, maybe it'd be less baffling. So let's try that. So this is equal to the eighth root of 5.8 times e to the I times 211 degrees. Now eighth root, we can write that as a power. So let's write that as a power. So what power is the eighth root? Hopefully we know it's the 1/8 power. And then we had that property where when you have a power outside of multiplication, you can bring that power into both of the factors. So let's do that here. So this is really 5.8 to the 1/8 times e to the I times 211, also to the 1/8. First term we're going to type in, first factor we'll type into the calculator in a minute. But the second one, again, we've got a nice property that says we can multiply the powers together. So this becomes e to the, or e times 211 times 1/8, which is just 211 over 8. Okay, that's good because now I've gotten rid of the 1/8 business. I've gotten rid of the eighth root business, and then I can just take this and go back into my x plus iy land. So this is 5.8 to the 1/8 times, and then we saw that the e to the I times 211 over 8, that's like an e to the I theta, which really becomes cis of theta. So that's 211 divided by 8 degrees. And that means 5.8 to the 1/8, and then cis really means cosine of the angle plus I sine of the angle. And I think all this stuff is just numbers we can type into the calculator. So just like that, using Eulers' funny formula, we have given meaning to taking the eighth root of negative 5 minus 3i. I mean, taking the square root of a negative number is already strange enough and leads us into the complex numbers. But what does it mean to take a root of an imaginary, of a complex number itself, as opposed to just a negative number in there? Well, this is what it means, and this is how you do it. So let's try to find this stuff on the calculator here. Okay, the 5.8 again was the square root of 34. I really need to save this number. Okay, so let's store that guy as r. Second, where's the r? There? No. Oh yeah, that's fine. And then I also wanted to store the 211. So the 211, no, it wasn't 211. It was the inverse tan of 3/5. And then we added 180. And then we're going to store this guy as theta, and theta is right there above the 3. Okay, so there's your r and there's your theta. So now we want to take that theta and divide it by 8. And we want to do cosine of that guy and sine of that guy. So let's go and store that one as, let's store that as c or something like that. So that's the 211 over 8. And then we need the 5.8 to the 1/8, so we can do that over here. So the 5.8 was r, so we can do second r raised to the 1/8. Okay, so that's the number that's in the front, 1.24 and change. Store that as D. I hope you're keeping track of all these letters. Okay, so then we need cosine of the angle and I sine of the angle. All right, so cosine of the angle. I think we called the angle C. That was this 26 business. So cosine of C is that thing. Then we multiply it by the 5.8, which we call D. We've got that number. And then, so that's the first part. And then the other part is going to be sine of the angle, also times D. So sine of the angle, that was C. And then we're going to multiply that by D. So if I've done all that right, then I think 1.11 and 0.55 are our two numbers when we do all the distributing here. Okay, so equals, what do we have? 1.1168. 685 is good, and then plus I times the other number, 0.553694. Okay, there you go. That is an eighth root of -5 minus 3i. It's a perfectly good complex number. Okay, can the calculator handle this thing too? I don't know, it's been doing so well for us. So what if we try? Let's see, what can we do here? So eighth root, I think we got to type the 8 first, and then we go into math, and then right there, number 5. So that stands for eighth root. And then what was it? -5 minus 3i. I think I needed parentheses here. Okay, 1.18. No. And then -0.398. I'm not feeling so good, gang. Maybe we made a mistake somewhere. Oh, no, that's right, the eighth root. Okay, so I'm back. Like no time has passed in the video, but about 20 minutes of my life have passed because I've been racking my brain trying to understand why what we got here is not the same as what the calculator gave us when we looked for the eighth root of this number. So I only just realized after 20 minutes of scratching my head that there isn't anything wrong with what we did. But I left this blank up here for a reason, and that reason is why the calculator is giving us a different answer. This is the easy but incomplete way. So to be honest, it's not worth a whole heck of a lot. And when we do the harder but complete way over here, then we will see the answer that the calculator gave, and we'll also see the answer that we gave, surprisingly. Harder but complete way. So there's a little bit more work here, not that much more, but a little bit more. So let's try this way. We're going to give a name to this thing that we're trying to find. We're trying to find the eighth root of -5 minus 3i. I'm just going to call it z. Z is the standard letter for a complex number, just like x is your standard variable. I'm going to multiply or take the eighth power of both sides. So this really means that z to the eighth is -5 minus 3i. So we're looking to solve this equation. And essentially this is kind of like, you know, if I asked you for the square root of 9, you could just say it's 3. But if you gave it a name, then you could square both sides and say, okay, you're looking for x values where x squared is 9. Now, this guy is just 3, but this guy, notice you get two answers, right? X is plus or minus 3. So we're actually looking for all of the answers. Well, at least it says a few other eighth roots. So we're going to find a few eighth roots, but there's more than one of them. And that's kind of the issue where we had the calculator give us one answer and we got another, and they're both right. So we're going to resolve that here. Okay, so we're going to start changing things. Instead of -5 minus 3i, we're going to write that in our polar version of things because that's more useful today. 5.8 e to the I times 211 degrees. And then over here we had z to the eighth, but we're going to rewrite z in some generic polar version of things. So let's go ahead and call that r e to the I theta, just as a generic name instead of z. So we're just going to say where z is equal to r e to the I theta. Okay, and now we're going to distribute, well not distribute, but we're going to let that eighth power come in and hit both of the factors here. We've done this before. So this is r to the eighth, e to the, and then the 8 multiplies by that power up there. So 2 steps in one, but this becomes 8 times theta times I, just shuffling the factors around. And then I'll copy this side. Okay, and now, now I'm going to start making things that look like they must be equal to each other or equal to each other. I see the e in both sides, and then I see a number in front of e in both sides. So I see r to the 8, and then I see 5.8. Well, I guess if we're going to make these equations true, then we better match up those two things. So r to the 8th is really 5.8. And then the other thing I see, there's e's that are in both, and upstairs there's i's that are in both. So the other parts are 8 theta and 211, and it sure seems to me like they're going to need to equal each other because everything else in this equation matches up kind of component by component. So I've got 8 theta equal to 211 degrees. Okay, and then we're going to solve these equations. So r is going to be take the eighth root of both sides here, so 5.8 and then the 1/8 power. And then over here we're going to divide by 8, so we get 211 over 8. And gosh, these things look quite familiar to us. 5.8 to the 1/8, that's exactly what we had out here. And then 211 over 8, well, that's exactly the angle that we got. So look, we've got exactly this thing. So how is this more complete? It doesn't seem to be any shorter. Or maybe it's a little shorter, I don't know. So here's the deal. We said that 9 has 2 square roots, +3 and -3. Well, every number has 8 eighth roots, and every number has 2 square roots. And so if we want to find any more of them, then we need to recognize that 211 wasn't the only angle that would have landed on that point. Let's draw a quick unit circle over here. So we had the point -5 minus 3i was right down there. -5 minus 3i. And we decided that 211 degrees was a reasonable name for this angle. 31 degrees is definitely not the right spot because we got to get in that fourth quadrant. But there are other angles that we could have picked besides 211. Couldn't we have gone around and said, okay, I'm just going to loop around once for fun, and then I'm going to go another 211? Wouldn't that have landed us on the same point? So add 360 to 211, we get 571. Couldn't we have done 571 degrees instead of 211? The answer is sure. And in fact, this will look familiar. We could have said plus 360 times any number, right? And we did stuff like this when we were solving trig equations not too long ago. We would say, all right, find the 2 fundamental angles and then tack on this plus 360k. We might have called it n. I don't remember what letter we used. So there you go. So then when we take this equation and we solve for theta by dividing by 8, we also need to divide this guy by 8, 360k over 8. And then we're going to change that to 11 over 8 plus, and then 360 into 8. What is that? So that goes 45 times, so 45k. Okay, so we're going to make a little chart. So what we're going to put in this chart are the different values of theta that we can choose. And then we're going to put, what are we going to put? R times the cosine of that theta that we chose, and then R times the sine of that theta that we chose. And then just for good measure, we're going to stick an I on this term because it's supposed to be R times cosine plus I, R times sine. Okay, so different values of theta we could choose. So 211 over 8, I'm just going to type that onto the calculator. So 26.375. Okay, that's fine. Or just as well, we could have let, maybe one more column over here, sorry about this. That's when k is equal to 0. But we could have let k equal 1, which just means adding 45 to that previous answer. So I think that gives us 71.375. Is that right? Or we could have let k equal 2, which means adding another 45 degrees to that thing, so 116.375. Or you could let k equal anything you want. I'm going to go up to 7, will be the last one. And I don't trust myself, so let's add 7 times 45 here. 3041.375. Okay, fair enough. And then we've got this funny r cosine of theta, and you know what, why don't I just erase the r's and put the numbers that they were, because the r that we ended up with was the, it's written right over here, it's this 5.8 to the 1/8, so let's get that on the calculator. Again, I want as much accuracy as possible, so I'll go back to my square root of 34, and then I'm going to raise that to the 1/8 power. If you want to be very fancy, you hit that button and that button, and you say take that. So this is the r that I want. So I'm going to erase this guy right here, and I'm going to erase this guy right in here. And I'm going to say this turns out to be 1.25-ish, 1.25, and then over here, I'll put the I at the end just because I'm running out of space. 1.25 times the sine of theta, and that whole thing was times I. Okay, so let's start doing some calculations. So I need this number here, so we're going to store this guy as r. Okay, so I need to do that number, the 1.25 r times cosine of the first angle, 26.375. And we get 1.168, so that looks familiar. That's the same thing that we got before. That was our first answer before. 1.1168, and then we'll do the same thing but cosine, but sine. And we get about 0.5538, which is what we got before as well. So that's one answer, and it's perfectly good, but then we'll get a different answer, like a really completely different answer by using the next angle. So let's do second enter, and then we'll change this guy right here to 71.375. Second enter, 71.375. So here's a different angle, a different answer, I should say. 1.18. 1.1813, and no, that was the y value. Let's try that again. 1.1813, and then the other one was a 0.3981. Okay, that's fine. Let's just do one more for kicks. So this one will do the same thing, but now we're doing 116.375. And we get those numbers. Is that right? I think that's okay. So we get the same answers as we got before, but one of them is a negative. So, oh, they've actually swapped places a little bit. 1.1168 is now over here, and then this guy is negative 0.5538. So there's a negative and they swap places. So there's some geometric thing that must be happening underneath the surface here. And then you can keep going and fill in as many as you want. There are a total of 8 of them. So once you filled this in, you'll have all 8. I guess I said I was going to put the i's next to each of these. So let's go ahead and put the i's next to them. So I, and then all the way down. And I think that this will resolve what we had written before. So I got this guy, which is the very first thing that we found. I said it's easy but incomplete because doing it this method, you're only going to get the one answer, this first answer in the table. But if you do it using this method, then you'll get all the answers, all 8 of them. Just takes a little bit more writing. Okay, so let's come back here, and the problem that I had was that when I typed in minus 5 minus 3i, and then I wanted to take the 8th root of that, that the calculator gave me a different answer. It didn't give me this blue answer. So let's see what the calculator says. 1.18 and then negative 0.39. That's interesting because I see the 1.18 right here, and I see the minus 0.39. Well, I see the positive of that number right here. Yeah, you can see the next couple of digits. Well, at least the next one matches up. Okay, so I think that if we filled in more of this table, I hope, that eventually we would find exactly this answer right here, somewhere in our table. So this is just one of 8 possible answers. Calculator can't give you all 8, and we have to do work for that. But you can get all 8 of them, including the calculator-based one, by filling in more of the table. Okay, so I just did the calculations here, and I saw that that the answer the calculator gave us is, in fact, the one that you would get if you plugged in 7 into our table. So I'm going to fill that in right here, 1.1813, and then negative 0.39 and change. And you can see the I at the very end of that. Okay, so it's a little bit of a process, this algebraic manipulation that we did to find the 8th roots of negative 5 minus 3i. There's an activity that follows. It will give you more opportunity to find some of these roots that we talked about here. So I'm hoping that you can emulate this process right here and find roots just like we did. And again, give the activity a shot before you check for the video. And the last thing that I'll say is that we did talk a little bit about how some of these numbers were repeated, like that 1.168 ended up bouncing over here, 0.55 came here, but it became negative. So I mentioned there's some geometrical thing that's happening there. And in this activity, you'll get an opportunity to explore the geometry of finding these roots of complex numbers.